do you mind if we open up with a quick look at Figure 2?
I can give you guys a quick tour of the office. Yeah, so I guess welcome to Figure. Yeah, we're
Thank
well
you.
over 100 engineers now. We're based here in Northern California, in the San Francisco Bay Area. We just unveiled last week Figure 2, which is our second generation humanoid robot. And we have, right now we're manufacturing about one a week in our facility here in California. And we have, several of them here now on the floor. So here's, a quick look at Figure 2 robot that we're about ready to start doing some tests on right now.
Amazing. I know your team is about to activate it. If you're going to say that the principal differences between Figure 1 and Figure 2, I mean, just for folks, the company's like 2 years old or less, right? You've gone from like 0 to infinity super fast. Yeah. What's the difference between what upgrades did you make in Figure 2?
There's several. So
your top 5.
Yeah, so I think first is we tripled the amount of CPU and GPU on board, just for more overall compute and inference. The second is we almost doubled the battery to about 2.3 kilowatt hours. It's all on board the system in the middle of the torso, here next to basically the compute and GPU. We had all the wires all internal. So there's no external wires, cabling, electronics. That's really for reliability and for overall packaging. We also have an exoskeleton structure. So all the outer shells of the robot actually take loads, which is opposed to kind of how we did the first generation robots. So this would be like more akin to how you would do it, like say aviation. My last company, Archer, we, the skins on the aircraft take the loads of the vehicle. So I think it's pretty unique here for a system like this. We also have 6 onboard cameras, so we have more perception, more ability to see our surroundings.
Where are the cameras on the robot here?
We have them in the head, in the back, and in the lower torso.
That's cool. And I assume that the exoskeleton helps you reduce overall weight of the robot.
Yeah, it's basically like overall, the parts will get a little bit stiffer as they get a little bit wider. We found that having one structure for both crash loads and stiffness is the right ideal mass trade. And Figure 1 had kind of like both structure and outer shell for loads. And that's just really not ideal where you, like the structure is really sized by crash loads. So then you end up having basically double mass in a lot of ways. Yeah.
And the hands, have you made improvements on the hands on the?
Yeah, so these hands here.
Hold his hand and show us what it looks like to view it.
These are our 4th generation hands now. And we've made like quite a lot of improvements over the previous generations. Better sensors, better packaging, better for mass, better strength, better speeds of the fingers. Overall, just better dexterity and control of like fine grain manipulation that we're doing on board the robot. We need to do like human-like applications. So the more here that we can do human-like tasks and grab human-like objects, the better for generalization of the robot.
Amazing. And it's standing, what, about 5'6", 5'7"
Yep,
behind you?
About 5'6". Yep.
Yeah, amazing. All right, thank you for the quick glance.